Hey everyone, at the top of this video I just want to say I lost the actual recording of me in the lecture hall. So this will be me going over the slides that I went in class. I'll give exact definitions and everything. It'll be just like you were in class. Also, I'll say that this was a shorter class. I didn't prepare quite enough. We're still kind of working the bugs out. But last we left off, we were doing some trigonometry. And I'm going to start out by doing a quick trigonometry example. So last time we were talking about this sort of rule that I always follow called SOHCAHTOA. And I've written this out in a bit more detail last time, and we're going to actually use this in this example. So let's say I have a point out in space right here, and it's a specific distance away in the coordinate system I'm using from the origin. So we're going to say that is R. Just a distance away. We're going to be using polar coordinates for this, so there's an angle involved also. Angle theta. Now the problem that we can sort of look at is I might know this distance R, and I might know the angle theta, but what if I wanted to find maybe the height of this point right here, or the distance from the origin? How would I find that? So distance from the origin will be this segment right here, x, and the height, above this axis, that will be y. Sort of the x is the horizontal and y is the vertical components. Now let's say I want to specifically find the height. So what is y? I'm going to put a question mark next to that. And let's say I have a value for r, so I have that value, and let's say I have this specific angle theta, and really I could solve the problem with that. Let's say I also have the distance from the origin x, sort of this horizontal component. So I have these three values, and I'm wanting to solve for the height. The height above, this could be like a height above the ground or something. It could be something important later on we need to solve for. Let me get rid of those check marks. So I have these three values, but I want to solve for y. That's where we're going to start using SOHCAHTOA. So this first term right here, SOH, that is just saying sine of the angle is equal to, so the other two, OH opposite over hypotenuse. All right, and this next term, ka, that is just saying C for cosine. Cosine of the angle is AH. So that's adjacent over hypotenuse. And the last term, TOA. That is saying tangent of the angle, theta, is equal to OA, opposite over adjacent. So I have in here, I didn't write out the full terms, so I have like adjacent and hypotenuse. I also have this word opposite. What do those exactly mean? So if you remember back from trigonometry, we're basically just saying these terms are just the sides of a triangle. So we have x, theta, and r. What are these, though? I have over here in the example opposite and hypotenuse. What exactly are these terms? So first we need to see which angle we have. So we have the angle right here. So we know this angle of this side of the triangle. So we know, I should specify this is a right triangle. So I should have that right there. So we have the angle, let me see if I could, we have the angle right here, and we have this side. What side of the triangle is this? Relative to this angle on this side. So this x, this horizontal component, is the adjacent side. And where's the hypotenuse of the triangle? That is always going to be this longer side for a right triangle. Okay, so we have quite a few of these terms. We have the adjacent side and we have the hypotenuse. So if we want to solve for this, that means we're solving for the opposite side of the triangle. So we want a term that has opposite in it. So this sign right here has opposite, and so does this tangent right here. It has opposite. And we just look at the other terms and we see, do we have those? So in my sort of example, I said we have theta and we have the adjacent side. So we could use tangent, this tangent equation, or we can use this sine equation because we have theta and we have the hypotenuse. So let's for the example, I'm going to use this sine equation. So I'll write it out again in full. So sine theta equals the opposite side over the hypotenuse. Now I'm going to write it as the terms of this specific triangle I see in front of me. So sine of theta is equal to, the opposite side is y over hypotenuse is, I labeled it as r. All right, so now if I wanted to solve for y, if I wanted to find out what this value is for y, how could I get this all by itself? I just multiply this r over to the other side. So we have y equals r times sine of theta. Okay, if let's say we do another example. I'm going to do it over here on the left side. And I'm going to take some of these values away from the triangle. So let's say I don't have y still. I'm going to erase that. And let's say I want to find theta right here. but I don't have y. I don't have this side of the triangle. I don't have this, but I do have the hypotenuse, and I do have this side right here, the adjacent side. How can I use these two to solve for the angle? So again, we're just going to go back to what we always going to refer to, SOHCAHTOA. We're going to look at what we have, and we're going to look at what we want to solve for. All right, so we have the hypotenuse and we have the adjacent side. And we want to solve for theta. So which of these equations has the adjacent and the hypotenuse in it? So adjacent and hypotenuse, the only thing that we don't know in this would be theta. So that means we could use this cosine equation to solve for theta. So I'm going to take that over here to the left side. So let me rewrite it. Cosine theta equals adjacent over hypotenuse. Let me rewrite it in the terms of this problem. Cosine theta is adjacent side to this angle is x over hypotenuse, r. But now you can see, we're at a similar spot to that other problem, but now we want to solve for the angle theta. How do we solve for the angle theta right here? Well, we are just gonna, the way I like to think about it is you're gonna divide over this first bit, the cosine, to the other side. So I'm gonna just sort of imagine taking that cosine term and dividing it over to the other side. And that will look like this. That will then turn into this. So theta, since I'm doing this, theta will be left on this side equals the inverse cosine of x over r. So this is just a function you can use in your calculator, and you just have this value and you take the inverse cosine of this fraction. And doing that will give you this specific angle. And pretty much if you're able to do this, if you're able to find the angle, and if you're able to find, any sort of side of this triangle, you can do, I would say, 90% of the physics problems. Like, not just in this semester, I mean, onwards. So this is just some very basic, relationships that will carry over into other semesters. Okay, moving on. Once we know we can do this, we're going to move on and we're going to see how we can actually use this when we talk about vectors. What is a vector, though? So we have a vector. Maybe you've talked about it in your math class, but I'll sort of go step by step in this explanation. We can start classifying things in the real world as one of two things. So if I go outside and I take a measurement of something, maybe I measure a building or I measure a road or whatever, I could classify it as one of two things. It can either be a scalar quantity or it can be a vector quantity. A scalar quantity is just a magnitude. So I'm going to write down magnitude. Just a magnitude. What does that mean? So it is just a number by itself. It will be a number and a unit. So if I was to count however many people are in a room, I'd say, maybe there's about 50 people in the lecture hall, typically. So that's just a number and a unit, 50 people. Or if I was to measure the temperature outside, it could be about 84 degrees Fahrenheit. It's just a number and a unit. So that's what I'm saying. It's just a magnitude. It just has a size. How does a vector act any different than this, though? Well, a vector is a magnitude So a vector has a magnitude and a direction. So it will have a size and it will have a unit, but equally important is the direction. So the direction is, as valuable as saying, how much there is. Well, what does it matter though? I have, what is an example of this? Well, if I was to walk somewhere, outside, I say I walked 1 mile today. A typical follow-up question is someone can ask is where? In which direction? Well, I walked 1 mile west, or I walked 1 mile this way and then also this way. So the direction is equally important, and it's this direction, since we're including this direction, we can now sort of think of things as moving. It's not just something walking. Imagine that walking example, walking on a treadmill. It's just a number, it's just a size, versus walking outside. You're walking actual distances in specific directions outside. So including this direction implies movement. Typically, a vector is drawn in your book or on the internet, wherever you find them. They'll just be drawn as an arrow. So let me draw let me first go like this. So we'll have a scalar. Say if I measure something and I get a scalar quantity. So I measure, I don't know, the size of a bookshelf or something. That will just be a scalar quantity. I'll say it is, from here to here. It could either be a line, or sometimes you might see like this. It's just a set length. I'm going to have it just as a line for right now. So we'll say that 6 meters, just for this example. As opposed to a vector quantity, the direction is always important. So I could have that same, segment, but the direction is important. It is pointing that way. 6 meters that way, but I'm also going to include the direction. Right here, I'm going to say, well, for me, that is going to be pointing east. But you see the direction is important. To show a variable, maybe in a word problem or something, shows that something is a vector, instead of saying vector this and vector that, add this vector and that vector. A lot of times it's just simplified to saying that you'll have a picture of a vector and it'll be labeled something, some specific variable. I'm going to call this one vector A. So vector A is typically labeled with an overhead arrow right above it. In a lot of different books, different authors, you might see a vector labeled as sort of boldface. I can't really do that on this slideshow, but it's just sort of boldface. That means a vector. So instead of this, it might just be the same thing but bolded. And then sometimes you might be given a vector, but you don't really care about the direction. Maybe the problem specifically just asks what's the size or what's the magnitude of a vector. So a lot of times you'll see something like this, a vector in between two absolute value signs, or within this absolute value sign. So it's just asking for the size or the magnitude of this vector. It doesn't really care which direction it's pointing. Okay. Now, why do we use vectors at all? Well, I kind of touched on it a bit earlier. It's because vectors will be, how we describe motion. We can use vectors just like we can with scalars. So if we have, however many people are in the room, I said about 50, we can just add another scalar quantity. We can just add more people, and the units combine. So instead of 50, I add 10 more people, scalar quantity. Now we have 60 people. It's still a scalar quantity. It's just a number and a unit. I could do the same thing with vectors. So I have to always remember that there is a direction involved with each vector though. So if I say I walked 1 mile west and then I walked 2 miles east, and if you think about it, those two directions are opposing one another. So the directions are important. I'll cover that in a bit, just a bit more. Okay, so we can add, subtract, multiply, and divide vectors. It'll be useful if we can learn how to do that. So an easy way for me to introduce this is to quickly go over the difference from distance and displacement. Typically, we have a lab on distance and displacement, but it was cut out this semester. So for distance, think of it as a scalar quantity. And displacement is a vector quantity. Okay, I'm going to add some, a sub-sentence to each of these. Distance, the specific direction or, way you're pointing does not matter. So, say direction does not matter. Displacement, direction does matter. how can I maybe show this in a picture? Well, I have a nice map on this next slide. Okay, so I have this little map of something I took off of Google, and I put 2 of these waypoints down, and let's just say that one of them, the one over here on the top left, is my house, and I want to go to the grocery store. It's over here, the bottom right. Now there are many different roads and paths I can take as I try to get to the grocery store, and all of them will add to my distance traveled. So you could think of the distance as just the odometer in your car. So that's this little gray thing. And that meter right there, it is always going to just be adding to itself. So, if I go from my house, I just take a path, somewhere down this way. Maybe I go that way. Over here, maybe there's traffic. Go around this way, there. There's a lot of turns in and out. The car itself does not care which direction you take. It's always going to count all of these turns. The direction does not matter. It's just going to count a total distance you traveled. If we look at displacement, the same map. For this, we have to consider the direction. The direction is very important. So we're going to, in your mind, try to imagine you take a picture of your car right when you start. So wherever your car is right when you start, and then you're going to take a picture of your car again right where you stop. And you're going to compare the distance between those 2 points. Okay, so the distance between these 2 is going to be this line in between. So the direction does matter, and it forms this sort of straight line path between where you start and where you stop. For this example, on why vectors might matter, let's say I have let's say I live right here on this number line, and instead of having a grocery store that's very far away and across town, basically, let's say I live right down the street from the grocery store, and I live right here. Let me do red. So I live right here on this point on the number line. The grocery store is all the way over here. And I'm going to say that each of these sort of divisions is 10 meters. 10 meters, so that'd be 20, 30, 40, 50, 60. So the grocery store is right down the street, and I want to go there and back. So I start out from my house. We do blue. So I start from my house. I go to the grocery store. What is the distance that I traveled? So distance is 90 meters. And what is the displacement that I traveled? So I'm going to say displacement. So I take a picture where I start, and I take a picture where I stop. Displacement is also 90 meters. okay, I'm done shopping and I want to go home. So I go from here all the way back home. Now we're going to consider this one trip. So there and back. What is the total distance that I traveled? The total distance that I traveled is 180 meters. What is the total displacement? So we take a picture where we start, we take a picture where we stop. So I started at my house, I go there and back, and I stop at my house. So my total displacement is 0 meters. So you can see how displacement being, it includes the vectors, vector quantities, is to show you that the directions do matter. If I add these two blue lines up here, if I add this blue line to that blue line, the directions themselves cancel each other out. So this is a very nice example. It is just in a straight line, there and back. We're seeing how the vectors will cancel. Things get more complicated when we move to, a bit more of the real world. We don't live on a number line like this. So we'll go to a more real world example. So adding vectors, just like how we're starting to do, how you saw in that last example, you can do them mathematically, so you don't need any pictures at all, or if they're done well, you can do them graphically, so just with the pictures. With that number line, you saw that those exact arrows were the same size. So theoretically, if the picture is drawn to scale, you can just use the arrows themselves to add the vectors. But let's move on to this. The sum of the two vectors is called the vector sum, or just the resultant vector. So what do I mean by this? Say we have a more complex example, vector A and vector B. Let's call this red one vector A. Let's call this blue one vector B. You see, it's not a number line. It's not, one way and then exactly opposite way. I'm moving with vector A at a slight angle, and then for vector B, it's, possibly flat. So what is the resultant vector? I'm going to have to add these two together. So I'm going to take a picture of where I start. It's going to be right here. And I'm going to take a picture of where I stop. Right here. And the distance between those 2 points is the resultant vector. So that's the vector addition. There we go. It's going to be this green arrow that I'm going to call vector R for resultant vector. What if I, well, let me write this first. So the resultant vector equals vector A plus vector B. All right, what if I switch the order though? What if I do vector B first and then A, like this? So this is the really nice thing about vectors. So remember, the direction is important. So even though vector B is second up here, so I'm just going to circle it real quick. Even though it's second, if I try to put it first, I still have to include its size and direction. So its size and direction remains the same. It's just, swapped orders. So let me get rid of the circle. So we have vector B down here and vector A. Again, take a picture of where you start, take a picture of where you stop. Picture where we start, picture where we stop, and you're going to find out that the resultant vector is exactly the same. So this is the exact same green dotted line, dotted arrow. So in math, that would be the same as, saying A plus B, vector A plus B equals vector B plus A. So it's just saying that the order that you include, the order that you arrange these vectors doesn't matter as long as it maintains its direction. Okay. So we're sort of introducing these more complex versions. We can find vector components of, just random vectors floating out in space. Say we're given a problem that's not, or maybe it's like, go from your home to the grocery store, but instead it's not a number line, it's, an obscure angle like this. We can break this vector up into its components to make it easier for us. So this is going to be vector A. That's what I'm going to call it. Let me make that better. Okay. Vector A, it's just pointing up and to the right, an obscure angle. It's made of a horizontal piece and it's made of a vertical piece. So let's say I sort of bring out a grid. So imagine there's like a grid behind it, horizontal and then vertical, like a grid. We can see that this vector is made of a horizontal component that I'm going to call A sub x. So that's just a small subscript x right here. So that's going from here to as far to the right it's going. So here to here. It's also made of a vertical component from here all the way to where it ends up here. That is what I'm going to call A sub y. So what you now see is I just created a right triangle, and thinking back to that trig example I was doing at the beginning, you see how valuable it is to know how to find the sides of this triangle right here. Maybe we're given the size of this vector A, and maybe this is a problem that's like I throw a ball so far that way, and it's I threw it that way with the size and direction of vector A. And the problem's asking how high above the ground is the ball. that's where we can then come in and say, well, it's going that way as vector A, so that means I can just find this side of the triangle to find its height off of the ground. So you can see how we might be using these later on. Alright, so that's vector A. Let's look at a different, more obscure one, vector B. Vector B, so we call this blue one, is made of its own components that are specific to vector B. So you can see it has, going from where it starts right here, it has a much more significant horizontal component. So I'm trying to go completely flat. I'm going to call B sub x as the horizontal bit of this vector. And if it were to have a vertical component, it will look like this. It's called B sub y. So we have these two vectors. Each vector has a horizontal, so here's horizontal components, and each vector will have a vertical component, A sub y and B sub y. You see we're going to get into where we might have to add vectors together. So let's look at maybe adding these two. So these are the exact same vectors from the previous page. We have vector A and we have vector B. And let's see here. I have two vectors that I want to add. Let me bring back those components from that previous page. So I'm going to redraw those triangles. So vector A has horizontal component that looks like this. It's called A sub x. And it has a vertical component called A sub y. Vector B, from where vector B starts to where it ends, it's called B sub x. And from here up to where vector B stops, it's called B sub y. Alright, so what we can do, let me put a little checklist over here on the left. I'm going to say first, for vector addition, I'm going to say break the vectors up into their component pieces, like how you see me have them right here, into their component pieces. Alright, and the next step is going to be add the like pieces. Alright, what do I mean by that? Add the like pieces. I think first, let me show you what I'm trying to achieve here. So where is the start and where is the stop? Where is the starting point and the ending point? So I'm going to start here, right at the beginning of vector A, and I'm going to end over here, vector B, the end of vector B. So remember, we're just taking two pictures. All right, so that will create a resultant vector that's going to be a line. Let me use this before I move the slide. So it's going to be a line from here all the way to up here. Right? It's going to look something like this. I sort of made the other two vectors transparent for this slide. But imagine now this resultant vector, the green one, I'm still calling that R, that resultant vector is just one long vector that is made of this. All the way from here to here, has its own horizontal component and its own vertical component. And let me bring back, or let me draw. I'll do it in blue. Let me draw those other, that previous screen's vector components on top of this. So we had vector AX was this, and you're going to see this vector B up here. Instead of drawing that dotted line up here, from here, I had a dotted line go all the way over. I'm going to have that line, I'm just going to draw it down here. Let me do it as, ooh, no, that'll be good. This will be good. For A, I'm going to do it in red, because that was the red vector. A sub x went from here to here, and B sub x went from here all the way over to here. And so that step that I was saying is add the like vectors. What this is basically coming down to is me showing you that R sub x is made of A sub x plus B sub x. And R sub y is made of A sub y plus B sub y. So that next, that second bullet point that I had said add the like components. So this is what I mean. So all of the x's, all of the horizontal components add together to form this new side of the triangle, this very large horizontal side. And once you do that, you then add all of the vertical components together. And after you do that, you'll get this very large vertical component for that vertical component of the resultant vector. And once you have the two sides of this large green resultant vector, you're able to use Pythagorean theorem and other trig values we discussed earlier. You see, we can find the length of this resultant vector by using the skeleton, or the pieces. We're using basically the pieces, A sub x and B sub x, using the pieces of the other vectors to find out how they will add together. and find out how this new vector will be oriented and pointing. Yeah. Let's move on to the next page. This one I didn't do too much on. It was just to show you how it can maybe get a little more complicated if I just keep adding vectors. I still have vector A, vector B, vector A and vector B, and then I added vector C. So where would the resultant vector be pointing? So take a picture from where I start. I take a picture where I stop. And it's going to be a line between the two. Before I move the page, let me sort of, again, clarify what I'm doing. So I'm going to break these up into their component pieces. That's always the first step. So vector A goes from here to here. That's A sub x. And it goes up to here. A sub y. Break up vector B into its component pieces. B sub x. And let me put it right here, B sub y. And then vector C is made of something slightly different. It is traveling downward. So that one will be C sub y, and then over to the right, C sub x. So before I, move slides, we can see that in order to get from, this point over here, in order to get from this point over to this point, I have to move a distance of ax plus bx plus cx. See, and that'll take me horizontal distance all the way over. Now let's look at the vertical components. In order to go from this point to this point, I have to move from here and go AY, up, and then BY has me go up a little bit more, and CY brings me back down by that much. So that's why I'm trying to show you breaking them into components and then combining them gets me to gives me a vector that looks like this. That has I'm calling it vector R again for resultant vector. Vector R is made of a horizontal component and a vertical component. And I'm always making right triangles when I do this. And this is where I can say all of the like terms are adding to create that that term. So Rx is equal to AX plus BX plus CX. And Ry is equal to AY plus BY plus CY. All right. All right, and I believe that is all of the vector material that I covered. I did move into Introduction to Motion. So let me show you the slides where I stopped, and you guys can write down this sort of informational slide details, but it's basically where I stopped last time. So topic 2 is motion in one dimension. In class, I'm going to have, let me go here. So in class, I'm going to have like a little carts moving on the table and a few physical demonstrations in class. But hopefully, hopefully my tablet works and the recordings work. So you can hear everyone's reaction sort of live. Otherwise, this is where I left off. If you guys have any questions, you could always let me know. Otherwise, I'll see you later in class. All right.